So in this mini lecture, let's delve in and talk a little bit more about the double slit experiment and add some equations to that experiment. So as you recall, this is what Young did. He took a card with two slits or openings and then shone a light on that card and then found that rather than having just an image with two lines of light on it, there was actually a series of lines or an interference pattern. And hopefully you were able to watch the video that kind of recreated this pattern. So if we look at what's happening, if you have the two slits, each slit is going to be a source of its own, according to Huygens principle. And then what we see is that the light is going to interfere. So we have places where it interferes constructively, and then places where it interferes destructively. So if we look at this, actually this image of the water, where the water is simulating the same interference that we see with the light and the double slits, notice that there are parts where the amplitude is highest. And then we also see places where the wave just completely cancels out. So if we imagine that this was light and we were to say put screen over here, then we would see a series of dark, dark, bright, dark, bright, dark, bright, and then there would be gradations in between. So you would see alternating bright and dark lines, which are a lot like what Young actually saw. So let's look at the math behind this. So remember that the what's important here is the path difference, because if they both start in phase over here, if the light from S2 is traveling further, so here's S1 and here's S2, if light from S2 is traveling, if they start in phase and it travels further, the amount of distance that it travels extra is going to determine what the phase is of this light versus the light from the other slit S1. So what we want to do is look at that path difference. And if it happens that that difference is exactly a wavelength, then it's not going to change the phase. These are going to both still be in phase and you'll have constructive interference. And again, for light, if it's constructive, that means it appears bright. If, however, the difference or the extra distance that this wave here from S1 travels is half of a wavelength, then that extra half of wavelength is going to shift everything over so that now the waves are out of phase by half a wavelength. Now they're going to cancel each other out and you're going to have destructive interference and you're going to end up with a dark line at that point. So let's look closer at the geometry so that we can look at this path length difference. We make this approximation that these are approximately parallel. That the light, and how do we make that approximation? Well, what we say is that the screen is far away compared to the separation D. So in other words, L is much greater than D. And so by saying that, we can presume that as this gets further and further away, these two rays are pretty much parallel. And so if we look at that and we consider this triangle here, let me see if I could redraw that triangle up here larger. So you have here on this, it's perpendicular triangle, here's theta. And then this is the path difference that we're interested in. We'll call it S2 minus S1, where it's little s is the path length. And then this is the separation D. We see that this path difference, S2 minus S1, is equal to D sine theta. So then if I look at trying to predict where the dark and bright lines are, for the bright lines, remember, if that path difference, d sine theta, so this is the extra, oops, excuse me, this is extra distance that the light travels. Oops, excuse me. Oh, wrong lecture. So this extra path distance that light travels right here, that's d sine theta. If it's an integer number of wavelengths, then you're going to get constructive or a interference or a bright line. But then if it's a half wavelength off, so in other words, if I take m plus a half, an integer plus a half, so if it's a half wavelength or 1.5 wavelengths or 2.5, then you'll get destructive interference or a dark line. So how does that translate? Well, notice that each one of those points where you have constructive at m equals 0, 1, 2, 3, you have a bright spot. And everywhere there's destructive, you have this dark spot. And then the lines in between are some gradation in between. So when we end up seeing, this is the intensity pattern as a function of distance. And here's the interference pattern shown in 2 dimensions. But what we capture on a screen over here is something like that. We see bright alternating with dark lines, and they're brighter in the middle. They get less bright towards the edges. And then, yeah, there's dark. And so they're pretty much regular. As you see here, they're all regular width lines. Now, one thing I want to point out is notice the dispersion in this lower diagram here. And where does that dispersion come from? Well, if you look at the equation, it says that for the bright spots, d sine theta equals m lambda. And you could do this, so if we look at that, m lambda equals d sine theta. So that means that the path difference depends on the wavelength of light. The path difference depends on the wavelength of light. So where it falls on the screen is in other words, you're going to get dispersion because of the dependence on the wavelength, d sine theta, but also where it falls on the screen is going to be important. So where does it fall on the screen in these problems? So let me just draw, actually on the next, let's go ahead and go to this one. If you notice here, it has, ignore these numbers, but again, for the white light, there's this, the light is all together, but then the different wavelengths get dispersed at different angles, okay? And that's what we see in this equation, that the lambda depends on theta, the angle of dispersion. So how do we relate that to what do we actually measure on the screen? Well, what we're actually measuring on the screen is we're actually measuring distances. So say here to the first bright maximum, we're going to measure this distance x. So if I look at a top-down view of this experimental setup, then I have over here, I have the 2 slits, and I have a light source. Then over here I have a screen, and then I have light coming over, and then on here I have the pattern that's on the screen. So I'm interested in this distance x measured on the screen from the central And then I notice that I can make a triangle here. And this is a right triangle. And it turns out that this theta is equal to that d sine theta. And so notice here that if this is L, the distance, then I have that tan theta is equal to x over L. So in this case, I'm looking at the path length distance in this equation. And then in this equation, I'm looking at the geometry of my setup to relate the distance on the screen to this angle theta. Now, I just said that that theta is the same theta. So let's take a look back at this setup right here. And so if you look at this theta, you can look at and see similar triangles. Okay, so if I were then to draw, let's see. So now on my triangle up here, let me draw a line going directly and so we have two triangles that have, if you look over here at this corner, you have this angle theta and then this complementary angle to theta. And so we see that this angle here adds to this angle theta to make 90, but also these two angles add to 90. So I could see that this angle here is theta. And this triangle is just a smaller version of an exaggerated one. So look here at the geometry right here in this problem. It shows you where theta is here. And you can see that because of the complementary angles at this corner, that theta is equal to that theta. So make sure that you prove that self to yourself, that trig is true. So what do we have here? We have our equations here, and in addition to this, we have that tan theta is equal to x, the position measured on the screen, over L. And so now we have all the equations that we really need to analyze these problems. Now there's one more thing to do, and that is to say there is something called the small angle. So I'm going to put it here. Because theta is very small, we can say that sine theta is approximately equal to theta, and tan theta is approximately equal to theta but where theta is in radians. So you have to make sure you're in radians on your calculator. Okay, so this is a useful approximation that we'll use because what you see here is tan theta equals XL. We can actually say that tan theta is approximately equal to theta, which is about equal to x over L. And we can also say that d theta is approximately equal to m lambda, and it simplifies our problems. So I would suggest taking a look at worksheet 9 and then trying problem number 2. And we'll do more problem solving on this in problem solving section. The last thing I just want to show is how the dispersion actually looks like. So again, because lambda is a function of theta, and we just saw that theta is the same theta that depends where it falls on the screen, then we can actually get dispersion. Okay, in the next video, we'll talk about diffraction around a single slit or some kind of obstruction.